It is genuinely funny how we experience modern air travel today.
Oh, yeah, completely.
Like, picture this. You're sitting in seat 12B right now, right?
Yeah, just trying to relax.
Exactly. You're cruising at some 5,000 feet, sipping this kind of lukewarm coffee, watching a movie on your tablet, and you're probably annoyed that the Wi-Fi is a bit sluggish.
Right, which is just amazing in itself.
It really is. And you are totally oblivious to the fact that just inches away, right on the other side of that thin plastic wall, you are basically suspended in the stratosphere by this invisible, heavily fortified electrical grid.
It is an astonishing environment when you really step back and look at it. I mean, we take the sheer magnitude of power coursing through the floorboards totally for granted.
Oh, absolutely.
You plug in your phone, you expect it to charge, you expect the cabin to be pressurized and warm while it's, minus 50 degrees outside.
Right, it's this illusion of total comfort. But today, for this deep dive, we're going to look at what happens when that illusion shatters.
Which is when things get really interesting.
Exactly. So
Yeah.
we are diving into highly technical engineering manual. It's an Airbus A320 electrical system masterclass, originally put together for senior flight instructors.
Yes, and the detail in it is just incredible.
It really is. And honestly, even if you never plan on sitting in a cockpit, understanding how these engineers design machines to survive cascading catastrophic failures, well, it offers this amazing lens into problem solving.
Yeah,
It's basically a masterclass in how to maintain grace under extreme pressure. So, to our listener, this applies to your life too.
The word I always use for this is resilience. The whole architecture of the A320's electrical system, it's not just about making the plane fly.
Right.
It is built entirely around anticipating the absolute worst possible day a pilot could ever have, and it ensures they have a mechanical or chemical or procedural answer already waiting for them.
Okay, let's unpack this, because
Okay.
before the bad day happens, I want to understand the normal day. So if I am in seat 12B, my tablet is being powered by the jet fuel combusting outside, right?
Yeah, ultimately, yes.
So how does raw jet engine thrust actually turn into a charging port at my seat? Give us the broad picture.
So it's this incredible chain of energy conversion. The A320 operates on two main types of power. First, you have this massive AC system, so 115 and 200 volt alternating current.
Okay.
But unlike the 60 hertz power in your house, the aircraft runs at 400 hertz.
Wait, 400 hertz? Why the massive difference from what we use on the ground?
It is all about weight. It basically comes down to physics.
Hmm.
A 400 hertz electrical system lets you use much smaller, lighter transformers and motors.
Oh, okay.
And in aviation, every ounce you save is fuel efficiency.
Right, that makes sense.
So providing this high-frequency AC power are two massive generators attached directly to the engine gearboxes on the wings. We call them integrated drive generator.
IDGs, right?
Exactly, IDGs. These are 90 kilovolt ampere workhorses. Just one of these could easily power several large homes at the same time.
Wow, okay.
And there's a third generator of the exact same size attached to the APU.
The auxiliary power unit.
Right, that smaller jet engine hidden in the tail of the plane.
Okay, so 3 massive AC generators. But a lot of the computers and sensors on a plane, they run on direct current, right? Like DC power.
Correct. So to get that, the aircraft routes the high voltage AC power through things called transformer rectifiers, or TRs.
Okay.
Think of a TR like the power brick on your laptop charger, but just on a massive industrial scale. You have two main 200 amp TRs stepping that 115 volt AC down to a stable 28 volt DC current for the flight computers.
Got it.
And what's brilliant is how quietly this is managed. If you look up at the overhead panel in an A320 cockpit during a normal flight, it's actually surprisingly dark. There are hardly any lights on.
Yes, the dark cockpit philosophy. I've heard pilots talk about this.
Yeah, it's a huge thing.
The idea is that a cockpit full of bright green, everything is okay lights is actually just a huge distraction, right?
Exactly.
So silence and darkness literally mean perfection.
It is brilliant psychological engineering. You only want to draw a pilot's attention to a switch if something actually requires their action. So in the dark, the system is managing itself using the strict automated priority logic.
Meaning the plane is making decisions on its own.
Basically, yeah. It is constantly asking, where should I get my AC power from right now? It always prefers its own on-site engine generator first.
Makes sense.
If it can't find that, it looks for the external power cord if it's parked at the gate. If that's not there, it goes to the APU generator in the tail, then the off-site engine generator.
Just keep stepping down the list.
Yeah, exactly. Down to the emergency generator, the RAT, and then finally, the absolute last resort, the batteries.
You know, it sounds a lot like a hyper-advanced smart home grid, like a house that seamlessly switches from rooftop solar to the city grid to a wall battery in the garage, and your TV never even flickers.
That's a really good analogy, actually.
But speaking of batteries, looking through these instructor notes, there's a very specific rule that seems kind of counterintuitive to me.
Okay, what is it?
So the plane has two main batteries. They're either 23 amp hour or 28 amp hour on the NEO models. But they are guarded by this thing called a battery charge limiter, a BCL.
Ah, yes, the BCL.
And it actively keeps the batteries isolated from the rest of the plane. Wait, why not just keep the batteries connected all the time like a car? Like my car's alternator's constantly trickling a charge into my battery while I drive.
What's fascinating here is that the car analogy makes total sense on the surface, but there's one major difference, and that is the stakes.
The stakes, right?
If your car battery dies while driving, you pull over. If an aircraft battery is compromised, you lose your absolute last line of survival.
Oh, I see.
If you leave the A320 batteries connected to the main electrical bus continuously, any kind of invisible electrical fault, say a tiny short circuit or a slow voltage drain, it could quietly bleed those batteries dry while the pilots think everything is fine.
Oh, wow. So you wouldn't even know they were empty until both engines failed and you desperately reached for them.
Exactly. It's the nightmare scenario. Those batteries are mathematically sized to provide a critical 30-minute essential power reserve.
Just 30 minutes.
Yeah, that is your ultimate safety net. So the battery charge limiter acts as a ruthless bouncer. It only connects the batteries if they specifically need charging, like if voltage drops below 26.5 volts.
Okay.
Or for an APU start, or if all AC power is completely lost below 100 knots. Otherwise, they just sit there, fully charged, walled off behind electrical contactors, waiting in the dark.
That is fascinating. The best way to protect the lifeline is to just not use it.
Exactly.
Okay, so that is the invisible grid working perfectly. But, you know, machinery breaks, an engine eats a bird, or gear wears out. If one of those massive 90 kVA generators just outright fails, does the pilot have to start frantically flipping switches?
Not at all. The automation absorbs that shock instantly. The moment a main generator drops offline, a heavy-duty switch called the bus tie contactor automatically slams closed.
And that does what exactly?
It physically reroutes the electrical pathway, so the one remaining engine generator crosses over and powers the entire aircraft.
But wait, we just established these generators are sized for specific loads. One generator can't possibly power the whole plane perfectly without overheating, can it?
Right, it can't. You're exactly right. It cannot handle the maximum potential load. So the system performs an automatic triage called load shedding.
Ah, okay.
In a fraction of a second, the computers instantly cut power to the galley.
So goodbye hot coffee and oven-heated meals in the back.
Precisely. The passengers might complain, but up front, the essential flight systems remain completely untouched. The plane plays favorites.
Aviation over hospitality.
Exactly. And the same seamless logic applies if a TR, a transformer rectifier, fails. Say TR1 goes down, the system just shifts the DC load to TR2 and an essential TR without the pilot lifting a finger.
That seamless redundancy is amazing. But this masterclass also highlights situations where the automation reaches its limit, right? Where a human actually has to intervene.
Yes, and those are highly specific procedures.
Let's look at the IDG disconnect. Say the oil inside that integrated drive generator gets incredibly hot. The manual says 185 degrees Celsius. Or the oil pressure suddenly drops.
Right.
The automation won't fix this. The pilot has to reach up and push a very specific button on the overhead panel. And reading this, it sounds exactly like pulling a parachute ripcord. You pull it, and you are totally committed.
That is a perfect way to visualize it. Pressing that IDG disconnect button initiates a violent mechanical action. Yeah, it fires a high-current solenoid that physically forces a set of metal dog clutches to separate. It literally decouples the generator's drive shaft from the spinning engine gearbox.
Oh, wow.
Once those metal teeth separate, that generator is offline for the rest of the flight. You can't just push the button again to reconnect it.
So you can't undo it in the air.
No, it requires a mechanic on the ground with tools to physically reset it.
It's a one-way street.
Yeah.
But humans make mistakes, right? Especially when alarms are screaming. What if a pilot panics and holds the button down too long or presses it when they shouldn't?
And this is where we see the strict limitations of human-machine interaction. The flight manual explicitly warns the pilot, you must never hold that button for more than 3 seconds.
3 seconds. Why?
Because it uses that high-current solenoid. If you hold it down, the electrical current will literally melt and burn out the solenoid coil, and destroying the disconnect mechanism.
Ouch.
Furthermore, the engine must be turning, either operating normally or at least windmilling in the air. If you try to disconnect it while the engine is totally stationary, those metal clutches are locked under tension.
Oh, so it just breaks.
Yeah, trying to force them apart while stationary will shear the metal and cause severe mechanical damage. Automation requires disciplined human interaction.
So the human has to follow the machine's rules, even in a crisis.
Yeah.
But again, human error. What if the pilot is completely overwhelmed?
It happens.
The 185-degree alarm is blaring, they're talking to air traffic control, and they just completely miss the warning. They don't push the button. Does the generator just keep heating up until the wing catches fire?
Airbus engineers anticipated that exact human failure, and their solution was to bypass software entirely and rely on the laws of physics. Built deep inside the IDG is a tiny solder fuse.
Wait, just a piece of melting metal?
Just a piece of specific metal alloy. If the oil temperature reaches 200 degrees Celsius, it hits the absolute melting point of that solder. The fuse physically melts away.
And that triggers something.
Yes, the melting of that fuse mechanically triggers a spring-loaded thermal disconnect. So even if the human freezes, chemistry and physics step in to permanently disconnect the generator.
I love that. A tiny 50-cent piece of melting metal saving a multi-million-dollar aircraft. The ultimate physical fail-safe.
It really is.
Okay, so we've seen minor failures handled gracefully, but let's escalate this. What happens when the absolute worst-case scenario hits? Both engines fail. Complete loss of all main AC power while you are flying at 400 miles an hour.
When both AC buses lose power and the aircraft is traveling above 100 knots, the plane senses this catastrophic loss and automatically drops into what is called the emergency electrical configuration.
Because right then, the plane isn't a highly automated marvel anymore. It's basically a 70-ton glider with no electricity.
Temporarily, yes. The instant that total power loss happens, a door in the belly of the aircraft physically springs open, and the rammer turbine, the RAT, drops out into the slipstream.
The RAT. I always picture this thing like a desperate last resort windmill popping out of the belly of the plane.
It essentially is a high-tech windmill. It's a propeller, about 31 inches across, driven purely by the rushing air outside the aircraft.
Okay.
The energy transfer here is fascinating. The wind spins the propeller. The propeller turns a hydraulic pump, which pressurizes the blue hydraulic system. That high-pressure fluid spins a hydraulic motor, which finally turns a tiny 5 kVA emergency generator.
Wait, 5 kVA. We started with two 90 kVA generators. That is a gargantuan drop in power.
It is a brutal reduction. At this stage, the system ruthlessly prioritizes absolute survival. That tiny emergency generator produces just enough power to supply the AC essential bus and the DC essential bus.
So no passenger lighting, no entertainment.
Everything non-critical is dead. But there is a terrifying catch to this sequence.
The gap.
The gap. From the exact moment both engines fail, it takes time for gravity and mechanics to work. It takes about 8 agonizing seconds for the RAT door to open, the turbine to drop, the blades to spin up, the fluid to pressurize, and the emergency generator to come online.
Here's where it gets really interesting. Just put yourself in that cockpit for those 8 seconds. The deep, comforting hum of the engines is suddenly just gone.
Replaced by the sound of rushing wind.
Right. The cabin goes completely dark.
Yeah.
A continuous, repetitive chime, the master warning bell starts ringing. On the overhead panel, a glaring red Fulton light illuminates.
Yeah, it's intense.
And for 8 seconds, the only thing keeping the flight computers alive so you can physically steer the plane are those 2 isolated batteries we talked about finally doing their job.
It has to be the longest 8 seconds of any pilot's career. And it underscores a massive transition. Because when the RAT finally comes online and that red fault light extinguishes, the flight has permanently changed. You've gone from monitoring a digital marvel to facing a raw physical test of pilot skill.
Which brings us perfectly to the human element, the crew dynamic.
Right.
The manual emphasizes this golden rule: fly, navigate, communicate.
How does the environment in the cockpit actually change here? Because they aren't looking at the same screens anymore, are they?
No, the visual landscape degrades drastically. The first officer's screens on the right side go completely blank, pitch black.
Wow.
Only the captain's side retains power. Specifically, the captain's primary flight display, the navigation display, and a backup called the ISIS.
The ISIS?
The Integrated Standby Instrument System. It's a totally independent little screen with its own internal gyros and backup battery. It gives the bare minimum pitch, roll, airspeed, altitude.
Just in case everything else fails. Exactly. And because the first officer is now blind, the captain is instantly forced to take over the physical flying, loudly announcing, "I have controls!"
And flying the plane is suddenly much harder now, right?
Significantly harder. Because the complex flight control computers lack power, the aircraft drops out of normal law and into what Airbus calls alternate law.
Alternate law. It sounds like a dystopian sci-fi movie. What does that actually feel like?
It feels heavy. In normal law, the computer smooths out your inputs. It auto-trims the aircraft so you don't have to constantly hold pressure on the stick to keep the nose level.
But in alternate law,
Those automatic conveniences vanish. The pilot faces heavy, raw manual control sources. They have to manually trim the aircraft. They are physically wrestling this 70-ton glider.
so the captain is sweating, manually flying. Meanwhile, the first officer, whose screens are blank, becomes the pilot monitoring.
Yes.
Their job is to look at the central screen, the ECAM, the Electronic Centralized Aircraft Monitor, right?
Yeah.
The thing that displays the emergency checklists using the ECP, the control panel.
Exactly. The ECAM is the central brain for troubleshooting.
So what does this all mean? Isn't it a massive waste of resources to have the first officer just reading off a screen while the captain wrestles the plane? Why not have them grab their stick and help fly?
If we connect this to the bigger picture, it seems counterintuitive, but having them both fly would be a recipe for disaster. This strict division of labor is a masterstroke of crew resource management.
How so?
In a life or death crisis, human cognitive bandwidth narrows dramatically. Tunnel vision. If both pilots are wrestling the aircraft, no one is solving the electrical problem, and no one is configuring the plane for landing.
Ah, so you separate the physical flying from the complex troubleshooting to reduce cognitive overload.
Precisely. Disciplined ECAM handling by the pilot monitoring is what prevents a bad situation from turning fatal, and they act as the ultimate cross-check. They must verbally verify any irreversible action with the captain before executing it.
Like pushing that IDG disconnect button.
Yes. Or pulling one of the red-capped wingtip breakers. The manual notes those red-capped breakers must actually never be pulled in flight because they permanently lock the wing flaps in place.
Yeah, I
Right.
see.
So if the first officer is rushing and reaches for the wrong switch, the protocol forces them to stop, point at it, and ask the captain for verbal confirmation. It breaks the chain of panic.
That is incredibly applicable to any chaotic work environment. Fly the plane, first stabilize the core crisis, then navigate, then communicate.
It is the ultimate lesson in prioritization.
Okay, so they've prioritized. The plane is stabilized on RRAT power.
Right.
But they still have to land this heavy glider. And this descent sequence, this is where the engineering gets almost unbearably tense.
It really does.
Because the RRAT relies entirely on rushing air to spin, right?
Yes, it needs kinetic energy from the wind.
So as the plane slows down to land,
Hmm.
the wind slows down.
Which means the RAT propeller slows down. This initiates a nail-biting sequence of controlled degradation. As they descend, the pilot must deliberately keep their approach speed fast above 140 knots for as long as possible.
What happens if they slow down too early?
The wind speed drops, the RAT literally stalls out, and they lose hydraulic pressure and their emergency generator while still thousands of feet in the air.
It is like watching a spaceship re-entering the atmosphere, methodically shutting off life support systems one by one to save the final drops of juice for the brakes.
That is a very accurate way to picture it. As the pilot finally lowers the heavy landing gear, creating massive drag, the aircraft slows down. Around 125 knots, depending on the model, the RAT simply can't spin fast enough.
And the emergency generator disconnects. So what powers the computers then?
Power falls all the way back down to our old friends, those two isolated main batteries.
Oh.
The battery power runs through a component called a static inverter, which turns flat DC battery power into a tiny bit of alternating current. Just 1 kVA of AC power.
Just 1 kVA. From 180 kVA down to 1.
Just enough to keep the bare minimum glass instruments alive to see the runway.
And it gets even tighter. Below 100 knots, the DC battery bus is recovered. But at 50 knots, the AC essential bus is automatically shed to save battery. Wait, the screens go dark while they are still rolling down the runway at 50 knots. How is that not terrifying?
It is a startling moment, which is exactly why this masterclass highlights it as a key debriefing point. You have to train pilots to anticipate that sudden darkness so they don't panic.
I would definitely panic.
But from an engineering standpoint, by 50 knots, the aircraft is firmly on the ground. Visual cues outside the window take absolute precedence. You're steering by looking directly at the painted runway center line.
And they drop into direct law on the ground, right?
Correct. Sophisticated braking computers are totally offline. No anti-skid protection, nose wheel steering is lost. The pilots have to use alternate mechanical braking powered by a separate yellow hydraulic accumulator.
And accumulate.
It's a pressurized vessel with nitrogen gas pushing against hydraulic fluid. It gives them a limited number of physical brake applications to bring the aircraft to a safe stop.
Unbelievable. From the deep redundancy of 3 massive generators, down to 8 seconds of battery power, to a windmill, to an inverter, and finally landing a 70-ton glider with blank screens, using trapped gas pressure to brake.
It profoundly changes how you view automated machinery.
It really does make you appreciate the invisible fail-safes in our lives.
And you know, the engineers hid brilliant lifelines everywhere, not just for total power loss. Consider this one detail from the instructor tips regarding smoke drills.
Okay, smoke in the cockpit, a nightmare scenario.
Right. If there is a severe electrical fire, the checklist tells the pilot to press the GEN1 line push button. This violently isolates the main generator from the main electrical bus to starve the fire of electricity.
Makes total sense.
But there's a risk. If you cut power to the main bus, you also cut power to the electrical fuel pumps. You could accidentally starve the jet engines of fuel while trying to fight a fire. So, the engineers wove a secret exception into the wiring. Pressing that fire isolation button intentionally keeps a hidden, direct, unmonitored power line open straight down into the wings, directly to the left and right inner tank fuel pumps.
Wait, really?
Yeah.
It bypasses everything.
Yes, a dedicated lifeline. The screens go dark, the pilot thinks they've shut down the grid, but deep inside the wing, the plane secretly keeps its own heart beating, pumping fuel to the engines completely off the grid.
That is incredible. A hidden string of electricity just to ensure the engines keep breathing when the rest of the ship is shut down. It really leaves you wondering, in all the highly automated systems we trust our lives to every single day, from our cars to medical devices to financial grids, what other hidden, unbreakable lifelines have engineers secretly woven into the code, just waiting to save us when everything else burns away? Next time you're sipping coffee in seat 12B at 35,000 feet, take a second to think about that invisible safety net holding you up.